guys, so I'm going to be solving LeetCode number 269, Alien Dictionary, hard, in C++. This is one of the more intimidating looking problems. I know a lot of people struggle with this question in particular because it just seems like it throws a lot in your direction, a lot of buzzwords, and a lot of different concepts at once. But if you really take your time and try and think through it logically, and I know that's kind of like a really general and umbrella statement to make, but in this case, taking a moment to think about it could really be your best friend rather than aimlessly going through and trying to think of random algorithms. So there is a new alien language that uses the alien English alphabet, but the order you don't know. But you're given a list of words, and the strings are sorted lexicographically by the rules of the new language. And we also, so we have this list of words here, which are sorted lexicographically increasing. What this means is very much the same thing as when you look in an English dictionary. Let's say we have the word apple, and we have the word application. This would be in lexicographically increasing order, because apple here and here, the same ordering of words as here, but because I comes after E, this word naturally comes after this word. That's what it means by lexicographically. But using the rules of this language, we don't necessarily use the rules of the English alphabet. So in this case, WRF, F comes after T. You can see this because WR and WR are featured before that. We don't know anything about what W and R are like. We just know that because these two are in the same order, the comparative words are T and F. So we know T comes before F. And so on and so forth. We have E here and we have E here, but we have R here and we have T here, which means that we know T comes after R. And we just go through this whole list, and we want to return a string like this, which contains the sort of alphabetically increasing, the alphabet in this language. In this case, W is the first letter, and then E, and then R, and so on and so forth. If it's not possible, we want to return an empty string. And I'll go over, there are a few different edge cases that we have to consider, but I'll go through the main logic of the algorithm first. Now, if you really think about it, we could consider these words, these letters that come one after the other, in the same way that we can consider nodes in a graph. They have their in degree, they have their out degree, they have their neighbors, and so on and so forth. So in this example, right, we know specifically that L comes, we know that E comes before I. That's what we've gathered here. But if we were to apply this to the dictionary, what do we have here? We have this list of words. Let's paste it here to do an example. Let's go through each word and try and gather the logic behind how we got to that output. So we start off with these two words here, W and R and W and R. So we don't know anything about W and R, but we know that they're both in the same word. So the lexicographic difference comes in the difference between the last characters. So we now know that F comes after T. So we can have this going like this, so that T is the parent character and F is the child character. We have an in degree of 1 now going into F through this relation alone. Now let's look between WRF and ER. So immediately we can tell that W is different to E. So we can have W pointing to E, right? W comes before E in this alphabet. What else do we have? R here and R here. So nothing else to do here. Now let's compare between ER and ETT. E and E, so same character, so the comparative character is between the difference between R and T here. So R comes before T, but wait, we've already established that T comes before F. So what if we just combine this relation that we've established earlier, which means that R comes before T, which comes before F. See, now we're forming the relationship here, we're forming the graph. You can see what I'm trying to get at here. So now we've done this. Now we have to do ETT versus RFTT. So E comes before R, because E and R are different here. It's the first differing character. But we already know that W comes before E, right? Because we've established this earlier. And then what else have we got? We've got R, and we know that R is connected to T, which in turn is connected to F. We formed the full alphabet, right? And there we go. Now, it makes sense now that we're going through this in a sort of anecdotal sense, but mathematically how this corresponds is we can look at the integrity between the differing characters in our graph. We're going to be using what's known as Kahn's algorithm for topological sorting of the graph, which is a common graph searching mechanism. It takes a little bit from Breadth First Search's playbook in the way that it's implemented, because we do need a queue in this case. But we have solved it in this case. How do we get to this point though? Just by looking at the strict relationships between all of these characters. Let's ignore the final result for now. So what we've got here, we've got R coming before T, and then we have ETT versus E going to R. How do we actually manage to establish the relationships? How do we, understand this? Because as it looks here, it just looks like we have isolated edges that don't really have a semblance of relation to one another. How does this F, for instance, know about the existence, or how does this E know about the existence of that E? How? Well, we have our integers, right? So T going to F, we know that F has an integrity of 1. We also know E has an integrity of 1, and we know that R has an integrity. We have integrity of 1, yeah, and we know T has an integrity of 1. But we also know that W has an integrity of 0, because nothing has connected to 0, right? Nothing is connected to W, so we know that W must be the natural logical starting point. So we can start off with our empty string, and we can go through our list of letters. We'll see, okay, which one has an integrity of 0. That means that this is the next point in our graph traversal. So we add this in. We look at W's neighbors, right? W is connected to E, which means that we can decrement E by 0, right? Because we've gone from W to E. That means we've made that integrity traversal. So now we can add in E, because nothing comes before E at this point. So we add in E to our queue. We then look at E, we pop it from the top of a queue, and we look at E's neighbors. What are E neighbors? R. We decrement R's integrity by 1. We then add R to the queue. What's R's neighbor? R's neighbor is T. Decrement this by 1. And then add T to the queue, because its integrity is now 0. Then pop T. We add that to the result. Look at the neighbors of T. Oh, it's F. Now we add in F. And then easy, right? That's one such example. Now, let me go through the second example, which may not necessarily be as straightforward. So, we have Z and we have X. Actually, this is even easier, right? Because we can say X and Z differ. They're the same length. Z has an integrity of 0, so that comes first. Then we pop off X, which is the only neighbor. That's the alphabet done. But what about this one? This one's interesting. Why? Well, because we have Z and we have X, right? Then we have X and we have Z, right? we have a cycle. We have a cycle. Exactly. Like, how do we know where to start from? We don't. There's no in degree of zero. It's impossible to really get a start. We've hit a cycle here, so we need to return an empty string. So we have to handle a few of these different test cases. Let's also think about another test case. Let's say we have, in the normal alphabet, we have A, B, C, D, and then we have A, B, C, right? In this case, we have absolutely no idea how D relates to the rest of the alphabet because we don't have anything to compare it to. If we have a longer previous character, which shouldn't really occur in this case, if we have a longer previous character with a D at the end or some other character, and this second word is entirely consumed into the first word, meaning that you can fit all the characters of the second word in the first word, then you have no idea how D relates to the rest of the alphabet, so it's impossible to build the alphabet in the first place, so we return the empty string in this case as well. Okay, so let's go over our code. Kind of makes sense. It will make more sense as I code it up. So first, I want to have an unordered map or any sort of mapping that goes from a character to a vector of characters. Let's just call this the graph. I also want to have an unordered map that maps every character with an integer, which will be the in degree, how many different things are connected to that if it was a node in a graph. So let's instantiate our graph first of all. So let's go through every word and go through every character in every word so that we can ensure that we have the full size. So for every character, we will instantiate an empty array, an empty vector in this case, rather. Also, we will set the in degree by default to 0. That's pretty standard. Now here's the bigger loop. Firstly, let's establish our result string right there. So let's go through the entire list of words. I'm going to do -1 and I'll explain why. We're going to compare like we've done in logical order, like I've done speaking to you, by taking pairs of words. So we don't want to overflow in the array. So it's best to do -1 in this case so that we stop at the end here. So let's say string word 1 is going to be equal to words I, and then we'll get the second string, which will be the word ahead. Let's handle the edge case right now. So if word 1 is a greater length than word 2, and word 1's consumes word 2, then we want to return the empty string. We can't form an alphabet in this context. Otherwise, we know we can get something. So let's go through another loop. And J has to be less than the minimum of the 2 words in our pairing. This is so that we don't go, overflow again. So J being less than the minimum of word 1's length and word 2's length. We then iterate J. And so if word 1J is not equal to word 2J, i.e. if the characters in the pairing differ at all, then we want to add in to word 1's graph of neighbors word 2. So word 1's character 1's graph of neighbors will add in word 2, character 2. We then also want to iterate character 2's in degree, because now we know that there is a neighbor that goes into it before that in the node, in the graph, sorry. Pretty simple. And we also want to break in this context so that we don't get any unnecessary duplicates. I'll explain what happens if we don't have this break statement by neglecting it for now and showing you the error case, the failed test case. So that is everything here. Then we want to have a queue of characters called queue. And first things first, we want to go through all of the int degrees. And if there is any int degree that is 0, that's going to be our starting point. So W in the first test case context. Okay, so now it's going to be similar to any sort of breadth first search. While the queue's not empty, we want to get the top character, pop it from the queue. We then want to add on to the result the character. And now let's go through all of the neighbors in that character, of that character. So we'll iterate through the graph of that character. We're going to decrement the int degrees of the neighbor. And if there's any int degree that's 0, we can add that into the graph, into the queue, rather. Okay, and now we can return result. So let's run the code first and check to see if it works. So it works for this test case. Now let's submit it and see what happens. Here is a test case that fails. Let me explain why as we go through it. So our expected result is ACBZ. How do we get a Z in this case? So we're going to go through the list of words. A and A are the same. C and B differ. So B now has an int degree of 1. A and Z differ. So Z now has an int degree of 1. Also notice that B and C differ in this case as well. We formed a cycle here, but we're not really comparing B and C here, are we? We're only comparing based on the first differing character. So the fact that B and C are less here, it doesn't really matter, because we're comparing based on strict lexicographic order, meaning that A and Z are the only thing that differentiates. Any character that comes after that doesn't make a difference. We only care until we get to the first differing character. So we formed a cycle unnecessarily when we didn't need to. So we want to completely break after we establish the first differing character. We're done with that word. We don't need to look through it any deeper. Otherwise, we're going to form cycles that didn't need to be there. Okay, there's still one more hidden test case. If I submit it here, we have B here, but the output should be 0. Why is that? So let's go through this. So Z differs to X differs to A differs to Z, and B differs to X. So let's think about this. Can you spot the error already? Z comes before X, so X has an int degree of 1. It actually has an int degree of 2, considering all things. A has an int degree of 1. And B has an int degree of 0. What else do we have? We have A, B, X, and Z. Z has an int degree of 1 as well. So let's start. We form our alphabet. B is our starting character. We then look at B's neighbors. B has a neighbor X. we can't access x. Why? Because there are two different characters that come before x. We don't know enough information to establish whether b comes before z or not, because both characters come before x. It's the same thing as saying that a comes before f and b also comes before f, but where does a relate to b? We don't know. We just know that both of them come before x. So again, this is another case where we can't form an alphabet, right? So in this case, if our result size, which is b here, this is the furthest we can get, if our result size is not equal to the size of all the characters, then we know that we've not gotten a full result, so we should return nothing. So that's easy to check here at the end. So we'll check, is the length equal to the size of int degree, which should have all of the characters as int degree. If it is, then return result. Otherwise, we want to return nothing because we can't form an alphabet. There we go.